Now, before I start working on examples, I want to go over one more thing known as the first derivative test. Now, I've actually already done the first derivative test in previous examples, but I never really formalized it. I just said, well, logically, here it is because, and that's what I did in the example. So let's formalize this idea of the first derivative test. Now, let C be a critical number of a function f that's continuous on an open interval containing C. If f is differentiable on the interval except possibly at C, that means that the first derivative could be undefined at C, then, this is what it's doing. This is defining all the critical numbers, is what it's actually doing. Then if f prime changes sign from positive to negative, because I should put those in quotes, as x increases through C. That's that left to right orientation. I'm passing through C left to right. Then f has a local max at x equals C. Well, if I draw a very quick picture of this, see my tangent lines have a positive slope, then a negative slope, hence I have a local max. If f prime changes sign from negative to positive as x increases through C, then f has a local minimum at x equals C. And again, a local minimum would look like this right there. Obviously, my tangent is going to go from negative to 0 to positive. And the reason we say except where C, except possibly at C up here, I could have this situation where I'm coming up and then do this. It's undefined here. The first derivative is undefined. So I have to watch that. So I'm still going to have positive slope, negative slope. So I still have a local max that will go with this idea. And the last point here is if f prime does not change sign, then f does not have a local extrema at C. Okay, so that is the first derivative test. So from here, we need to take a look at a couple of examples and put it into play.